Alright, so today we are basically looking at parts of circles. So we have a minor arc. There's going to be an arc formed by a central angle less than 180 degrees. So a central angle is going to have a vertex in the center of the circle. So it's an angle coming from the center, kind of like a piece of pie or piece of pizza. And so when that angle is less than 180 degrees, that arc, that portion of the circle that's in between the sides of that angle, would be called the minor arc. And then an arc formed by a central angle larger than 180 degrees is a major arc. So when we look at this angle here, on this side it's an acute angle, and on the other side, if we look at this as being 360 degrees, this is a whole lot more than 180 on this side. So that makes this side of the arc a major arc, and then the little part inside here the minor arc. Semicircle is an arc whose endpoints are the endpoints of a diameter, or basically, since a diameter cuts a circle in half, it's going to be half of a circle, a semicircle. And measure of a minor arc is going to be the same as the measure of its central angle. So if we know what the measure of the central angle is, then we know what the measure of the minor arc is. And the measure of a major arc will be the difference between 360 degrees and the measure of its associated minor arc. So basically, if we're looking here, we know what the measure of the minor arc is. We subtract that from 360, and that'll tell us what the measure of the major arc is. And congruent arcs are going to be two arcs of the same circle or of congruent circles that have the same measure. All right, since these measures are in degrees, those circles have to be the same size, right? Because I could have a really big circle with a 27-degree arc and a really small circle with a 27-degree arc. And just because both arcs are 27 degrees of the 360 doesn't mean that they would be congruent, because the circumference of those circles would be much different. Right. All right, so postulate 26, the arc addition postulate. We've already had a few of these addition postulates through here, the segment addition postulate, angle addition postulate, now the arc addition postulate, which is basically saying measure of an arc formed by two adjacent arcs is the sum of the measures of the two arcs. Or if I have one big arc that's divided up into parts, if I add the small parts together, I get the measure of the big arc. Theorem 10.4, in the same circle or incongruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So here it's basically saying if segment AB right here is a chord, segment CB is a chord. If these two chords are congruent, then the arcs associated with those chords would be congruent as well. So if within the same circle or in congruent circles. So the arc associated with the chords will be the congruent as long as the chords are congruent. All right, theorem 10.5. If the diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So if I've got a diameter here and it's perpendicular to a chord, making a right angle with that chord, then in order for that to happen, it has to be splitting the chord in half or bisecting it. And along with that, it'll also be bisecting the arc associated with that chord. So it's going straight down the middle of it. Which this rule, it doesn't say it, but it would actually also work with a radius, because the radius is going to come from the center through there as well. All right, so if one Theorem 10.6, if one chord is perpendicular bisector of another chord, then the first chord is a diameter. Right, so if we've got a chord that is a perpendicular bisector of another chord, then we know that that first chord has to be a diameter of the circle. So 10.5 and 10.6 are just converses of each other. Right. And then theorem 10.7, in the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. So if I've got two chords that are going to be congruent, then if I measure the distance from the center of the circle to the chords, those should be the same. All right, so EG and EF have to be congruent for chord CD and chord AB to be congruent. And remember, they're right angles here because if we're measuring a distance from a point to a segment or point to a line, we want that perpendicular distance because that's the shortest distance between the two. All right, questions on any of that so far? A lot of information there. All right, so here we want to find the measure of each arc. So first off, I want to find the measure of arc CB, which the only number they've given us is that arc C, or central angle CD, is 148 degrees here. And so if the central angle is 148 degrees, remember we learned that the arc will have the same measure as the central angle. So that means, get my pen to work. Maybe my computer will work. So if the central angle is 148 degrees, then arc CD is 148 degrees there. And so if we notice that this segment here, BD, it's a chord, and it's going through the center of the circle, which is A. So that means that BD is a diameter, and a diameter splits the circle in half, right? So it makes a semicircle or half a circle, which means that from B to D here, it's going to be 180, half of the circle. So for CB, that's going to be 180 minus the 148 for arc CD, 32 degrees. Then arc CDB, so this is going to be a major arc, and usually when we're dealing with a major arc, we're going to have three points listed in the arc just to make sure we know that we're going all the way around. As CB, we know is the minor arc right here. If I said CB and meant this arc right here, we wouldn't know what that means. So usually there will be another point in that major arc if we're going to name the major arc so that we know we're going this way to get from C to B. All right, so CDB is the whole circle except for CB, right? Or since the whole circle is 360, CB is 32, we can subtract that from 360. We get 328 degrees. then for BCD, of course we already kind of discussed that. BCD is just this half of a circle, right? So it's going to be 180 degrees. Alright, so then find the measure of each of these arcs. So arc BD, we got two arcs, or we know their central angle measures are 60 and 82. So those central angle measures get transcribed to be the same as the arc measures. So we go from B to D, I have 60 plus 82. 142. And then we've got angle BED, which basically we know that BED is everything except for BD, right? We just figured out BD is 142. So BED is going to be the 360 minus the 142. Should be 218. And then for BE, just this section, that's the only one that didn't have a number on it. But we just figured out BED, which is 218, and we know that DE here is 98. So if I take the 218 and subtract 98, that'll give me 120. Of course, another way we could have looked at it is that CE here is a diameter, and BC is 60. So we could have taken the 60 away from 180 and also gotten 120. So two different ways we could get there. We could get there with the information they gave us. All right. So next, find the measures of arc AB and arc CD. Are the arcs congruent? So when we look at these, measure of AB, since that appears to be a central angle, then AB should be the same as the central angle, right? Should be 60 degrees. Measure of CD also appears to be a central angle, so it should be 60 as well. And so there are two arcs, same measure, in the same circle. So that would mean that arc AB should be congruent to arc CD. All right, so then part B, we got the measure of AB here. It's going to equal 135. We have a central angle there, so the arc's the same as the central angle. Measure of CD, which is in a different circle, also has a central angle of 135. 135 degrees. So would those two arcs be congruent? They're both 135 degrees, but they're in different circles. So if they're in different circles, what has to be true about the circles? They have to be the same size. They have to be congruent circles, right? So is there anything in there that tells us that those would be congruent circles? If we look right here, if this is a central angle, then each one of these parts of that angle are a radius. And so if this radius marked congruent to this radius, so that's actually the information that's giving us to tell us that those two circles are congruent because they both have the same radius, right? So since the radii are congruent, that means that the circles are congruent. And so therefore, since these have the same measure, those arcs are also going to be congruent. So arc AB congruent to arc CD. Alright, so then next one for AB and CD. These are concentric circles. 210 degrees on the back side of this angle, which means the inside is going to be 360 minus 210. Which will be 150 degrees for that interior angle, or the central angle. Which means that those two arcs are both 150 degrees. Measure of arc AB is 150 degrees, and the measure of arc CD is also 150 degrees. So would those be congruent arcs? Why not? Alright, so they're off of the same central angle. They're the same measure, but there's a big difference in the size of the arc, right? The circle is much smaller than the outside circle. So just because this is 150 degrees of the small circle doesn't make it the same size as 150 degrees of the big circle. So this one, we would say that arc AB is not congruent to arc CD because the two circles are not the same size, even though the arc measures are the same. Alright, so you use theorem 10.4 to find the measure of arc BC. So theorem 10.4, refresh our memory. In the same circle or incongruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So if the corresponding chords are congruent, the arcs are congruent. Or if the arcs are congruent, the corresponding chords are congruent. So we've got BC marked congruent to BD. So that would mean that this arc is going to be congruent to this arc. Arc BC should be congruent to arc BD. So in order to solve for the x, which it's not just asking us to solve for x, it's find the measure of arc BC. So we need to find the x and then plug it in, figure out the measure of BC. So, but we do know that since those chords are congruent, the two arcs are congruent. So to start off, we're going to say 3x plus 11 equals 2x plus 48. Subtract 2x. X plus 11 equals 48. Subtract 11 from both sides. So our x value is 37. And then for the measure of BC, that's going to be 3 times x, which is 37, plus 11. 3 times 37, 111, I believe, plus 11. So the measure of arc BC is going to be 122 degrees. All right. So the last one here tells us that the length of AB is 12, the length of DE is 12, and the length of CE is 7. Find the length of CG. All right. So AB is 12, DE is 12, and CE is 7. And it wants us to find CG. So one thing we know about CG here is that it's basically the distance from C to segment AB here. And AB and DE are congruent. So this kind of relates back to theorem 10.7 here that told us in the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. So if we have congruent chords, they have to be equidistant from the center, which tells us that the length of CF is going to be equal to the length of CG. Now, since things are really slow today. Alright, so since we know that DE is 12, and this segment right here, CF, is coming from the center of the circle, if we extended that out, extended that line, that would make it a diameter, right? Since it goes to the center. And so since this segment right here, which could be part of a diameter, is perpendicular to this chord, we can use another theorem we just learned, which says that if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord. So if we look at this segment as part of the diameter, since it's perpendicular, we can assume that it bisects this chord. So since the whole chord is 12, each portion is going to be 6. Which tells us that we have a triangle right here, triangle CFE, that since there's a right angle on this side of it, we know that's going to be a right angle on the inside as well. So we've got a right triangle, and we have two side lengths. If we can find the length of CF here, it should be the same as CG. And so to find the length of CF, we're going to use Pythagorean's theorem. Since we have two side lengths of the triangle, and it's a right triangle, we can find the third. So Pythagorean's, c squared equals a squared plus b squared. C is the 7. 7 squared is going to equal the length of CF squared plus 6 squared. So 7 squared is 49. CF squared plus 36. Subtract 36. That gives us 13 equals the length of CF squared. And then take the square root. So the length of CF is going to be the square root of 13. And since CF and CG should be congruent, once we know what CF is, we know CG is also going to be the square root of 13. All right. Questions, anybody? That one's kind of difficult because we have to incorporate a couple of different theorems or different rules into it to get there. But, no questions?